Any questions? Okay. So what's going to happen, given that circuit diagram over there, we're going to solve it the way we did 2 days ago. And then I'm going to use this as an introduction to two different techniques to also solve it. All right, so the technique that works reasonably well, if I just have one power supply, is first to find the equivalent resistance. So what is the equivalent resistance? Or which two would we tackle first?
4 and 2.
And parallel or series?
Parallel.
All right. So 1 over the equivalent resistance of the 2 ohm and the 4 ohm would be 1 over 2 plus 1 over 4. That's 3/4. And so R24 is equal to 4/3 ohms. So we've taken this and we've reduced it down to, got my 12-volt power supply, DC power supply. I have a 4/3 ohm resistor, and I have a 6 ohm resistor. So basically taking that and sticking a 4/3 ohm resistor in its place. Now what?
Those are series. New series.
Okay, and how do you deal with resistors in series?
Just add them.
So this will then become 7 1/3, 22/3. Just think 7 1/3, so 7 is 21/3, so yeah. Still good, 22/3. All right. What is the current flowing out of the power supply, or how would you find it?
Ground law.
Yep. That tells me delta V equals IR. If we're talking about the entire circuit with a single power supply, that's the voltage of the power supply, that's the current coming out of it, and that's the equivalent resistance. If we're talking about a single resistor, then it's just the voltage drop across that one resistor. So we have 12 is equal to I times 22/3. So I is equal to 36 22nds, which is 18/11 amperes. And presumably, if I were doing this with a calculator, I would come out with some decimal value, but I know some people prefer fractions because I'm not rounding, at least not there. All right, so we are making the claim that the current flowing out of the power supply and into the power supply is 18/11 amperes. If we think about the initial circuit, which resistor has 18/11 amperes flowing through it? Yes, it is. Luis was not even here to hear the question, but he's now going to tell us the answer.
What was the question?
Oh, you're supposed to do it without knowing the question.
Oh, well, amps.
All right, he got part of the answer. No, he didn't, sorry. The question is, we have, the original circuit is the one in the upper left-hand corner. We've established that 18/11ths of an ampere is flowing out of the power supply, and the question is, which resistor has 18/11ths amperes flowing through it?
It's not.
Yes. Because any current flowing through the power supply here, well, there's no place for it to veer off. I mean, whatever's flowing through here has to be flowing actually all along here. Because there's no place for the current to go elsewhere. What's the word I'm looking for? In farming, when you've got a main river, then you do little channels into your crops that sort of come off the main river. Something ditches. You're looking at me like you have no idea what I'm talking about.
Irrigation?
That's it. So if you think about this is a water supply here. There are no irrigation ditches that are anywhere off to the side for it to go and feed the crops. I'll work on the analogy, it'll be better next year. All right, so if I've got 18/11ths of an ampere flowing down this bottom path here, and therefore through the 6-ohm resistor, what is the potential drop across the 6-ohm resistor? Or how would you find it?
What's the question?
If I've got 18/11ths amperes flowing through this bottom section, before it splits or after it joins up, or joins back up, what is the potential drop or potential difference across the resistor, that 6-ohm resistor? Or how would you find it?
Ohm's law?
Yes, that's a generic answer to a lot of this stuff, Ohm's law. So therefore, the potential drop across that 6-ohm resistor would be the current times the resistance, that's IR. And units?
Volts?
Sorry?
Volts?
Yeah. So, since I'm now dealing with 11ths here, since I'm dealing with fractions, this is 121, 133 11ths. No, that's not right. 12 times 11.
132.
132. So if, and again, sum of gains and losses has to be 0. I'm going to start here. I'm going to go across my power supply from the negative to the positive side, so I gain 132 11ths of a volt. Come up here, I'm going to lose something, either path, I'm going to lose something. Come down here, and I know I'm going to lose 108 11ths. Therefore, how much is lost from here to here? Or I should, from that junction to that junction, going this way, or that way. how much am I going to lose? What is my potential difference here?
24 11.
Yeah. So 24 elevenths of a volt. From this junction to that junction. No matter which path I take, they're in parallel, the potential difference is going to be the same. So we can now find the current flowing across here, and we can find the current flowing across here. And how do we find it?
Ohm's law.
There we go. Unison would have been incredible there.
Next time.
Yep, next time. And again, Ohm's law is the potential difference is equal to the current times the resistance. And so why don't we take the top one first? So we have 24 elevenths is equal to I times 4. Doing the fancy math here, I must be 24 44ths. Or 12 22seconds, or 6 elevenths amperes. That's the current flowing across the 4 ohm resistor. Across the 2, current flowing across the 2 ohm resistor is going to be 12 elevenths amperes. I know it's got to be doubled. Doing that more formally, using Ohm's law, I have 24 elevenths is equal to I times 2, and so I is equal to 24 over 22, which reduces to 12 elevenths amperes. We can now check. That's right, we started on the, not that I wasn't forgetting stuff when I was in my 20s, but, you know, at some point I'm going, is this an age thing or is this just a me thing? Because we set up the problem and never quite finished the complex one.
Yeah.
We'll get back to it.
I was wondering if that's what this was. I
No,
thought-
no, I.
Perfect.
So for all those international fans out there watching on YouTube, hey, the class says hey, even though they're silent about it.
Bonjour.
And we'll get back to the cliffhanger at the end of last class. Did you want to say something?
I said bonjour.
Oh. We can double check ourselves. The fact that I've got 12 elevenths going across here. I have 12 elevenths of an ampere flowing across there, and I have, that would be, that's 12, 12 elevenths there and 6 elevenths there amperes. That's flowing out of that junction and into this junction. So whatever's flowing out must be what's flowing in, so I have 16 elevenths and 12 elevenths, which is 18 elevenths, which is, hey, what we figured out was going into it. So, just a quick check. Connecting it with that problem that we were doing yesterday. If we did the whole thing in fractions, we should get exact answers. However, fractions sometimes are just a pain, especially when you have a calculator. So that's why we're going to take out the 4 decimal places. And I know I wrote down what we had done. Yeah, I might have to, that'll probably be faster than mine trying to find it in my notes. Or maybe I'm just imagining that I copied it down somewhere. Something different. All right, questions about this before we deal with? All right. I'm operating at about 3 or 4 hours sleep now,
Uh-oh.
which is only 1 hour less than what it usually is.
Huh. It's not healthy.
I was gonna use, you know what, I'm gonna continue with this. I'm gonna finish what I was planning to do on this one and then come back to that one. All right, questions about this? It's very similar to what we did yesterday and actually completed. Okay. A different technique for solving this. There's two different techniques. One of which is you are going to, since we're trying to find the currents, we're just going to start out making up values. One value, we're going to use variables between junctions. So this is one current per wire technique, and the other one is going to be one current per loop, also known as mesh analysis. So the way we do this technique is we get the diagram here. There's no finding equivalent resistance in this technique, for better or for worse. So that's 2 ohms, 4 ohms, 6 ohms, 12 volts. I have, well, how many junctions do I have in this?
Do we count both ends of the junctions? Or just
A junction is anywhere where current can split or join.
so 2?
Yeah. We have 2 junctions. I have 3 different paths to get from one to the other. So I am going to assume I've got 3, I'm just going to be clever and use I1, I2, I3. Now, it does not matter the direction that you write these currents that you are pretending are there. You can, in this particular example, you can figure out the direction the current's actually going to go, or you can just randomly put stuff down. So what I'm going to do is I'm just going to make everything go off to the left there. I'm going to call that I1, I2, and I3. I have 3 unknowns, I need 3 equations. First equation is the simple one. Pick a junction, doesn't matter which one. Pick one of them. The currents flowing, the sum of the currents flowing in equal the sum of the currents flowing out. Well, I have, I forgot to draw my arrow there. I have 3 currents flowing into this junction on the left here. So I have I1 plus I2 plus I3, and that is equal to the currents flowing out. And I don't have any, so that's equal to 0. One equation down, 2 to go. So in this technique, one of the equations for each, so I'd say for each junction there is an equation, but it's not quite that. For each junction pair, I guess, there's an equation, there's one equation. All right, next. I have 3 different loops I could go through. Actually, I have an infinite number, but 3 simple ones. Starting anywhere, but I typically start just before the battery. I can go down this lower loop, or I could go around the top loop, or around the whole loop, or I could just do this loop up here. So I've got this loop, and the whole thing. I need 2 of them. If I used all 3 of them, I'd end up with 3 equations, but only 2 are independent. I can always derive the third one from the 2. So this is going to provide me the 2 equations. So what do you do? So the junction rule, or the current rule, Kirchhoff's of course, gets me that one. The voltage or loop rule will get me the other 2. I'm going to start here, and I'm going to go clockwise. I'm on the negative side, that's the positive side of the battery. As I go across it, coming to the left, I go from negative to positive, so I gain 12 volts. Cruising right along, I'm gonna take the bottom route here, I'm now gonna go across the 2 ohm resistor. If I'm going with the current, because the general idea is current flows downhill, so it flows from a higher gravitational potential to a lower gravitational potential, if we're talking about water. But because I said the current was going this way, it's like I'm going upstream. So plus 2 times I2. If I were going with the current, it would be minus 2 times whatever current I said. But since I'm going against the current, I add. Coming along, then come down to the 6 ohm resistor, I'm going with the current, so I'm flowing downhill, so I'm gonna lose 6 times I1. And that equals 0. Now my other equation, there are 2 more equations I can pull from this, of which only one is useful. Doesn't matter, one of them is useful. I'm gonna start here again, and I'm gonna now take the outside loop. So I gain 12 volts. Cruising along, come up here, now I'm going across the 4 ohm resistor against the current that I assigned, so that's plus 4 I3. Coming along down this way, across the 6 ohm resistor in the direction of current that I said, so minus 6 I1 is equal to 0. I now have 3 equations, 3 unknowns. For those of you who use the TI-80 whatever calculators, years ago, Mike Jones created a document about how to actually solve this using those calculators. I do not know how to solve it using those calculators. I will show a different technique to solve it. Now, the advantage of the calculator is it saves you a whole lot of math work. The disadvantage is there really is no partial credit, because I see what you started with, I see what you ended with,